Thank you. Yes, so in this talk, I want to present another package manager called Spec. Let me give you a short outline. I will first motivate what we're coming from, what our background is, what we need. Then I will introduce this package manager called Spec that will include a short live demonstration. Afterwards, I will talk about a bit more about our specific setup and then briefly summarize. So what is our background? We're running the HPC high-performance computing system at our institute, and one of our tasks is to provide the full software stack on that institute, so quite similar to the talk that we've just heard. In our case, the software stack consists of two things. First of all, we have some precompiled packages that people can just use. For example, we provide Python or a density functional library called Octopus. And then we want to provide so-called toolchains, combinations of compiler, MPI, and some other dependencies that people can use to build their own software. And on the HPC, we want to expose the whole software stack via environment modules, which is the de facto standard on HPC systems, so people don't have to know anything about the underlying mechanisms. We would like to have the ability to install the same software stack locally. For example, people can compile one of these toolchains on their laptop and then develop software for the HPC in an environment similar to what they will find on the HPC. And of course, we would like to automate the whole process. The final setup on the HPC looks as follows. If we just have a look at what the users see, they can use the module command as they used to. If we run a module avail, we get access to a few different compilers here. And then as an example, I've loaded one of the GCCs. That gives us access to the software compiled with that GCC. And I've also loaded an MPI implementation here, OpenMPI in a specific version. And we get access to also the packages with that OpenMPI as a dependency. Why do we need to talk about this at all? Well, installing software is actually not so easy. If we want specific features, we can get optional features, optional dependencies for many packages, but each package has its own syntax, its own way of activating or deactivating these. And there are various different build tools that packages use. There are plain make files. That gives the package also a lot of freedom. And there's little standardization. There are more structured approaches like using AutoTools or CMake, but there is still a lot of flexibility for the package authors. And then there is a really big problem, that's dependencies. Typically, we need very specific versions of dependencies, and we need very specific features of these dependencies. And for anything that's a bit more complex, we typically have a large stack of dependencies. And fulfilling all requirements of all dependencies for a larger software stack becomes extremely tedious. So we can't really do this manually. Instead, we use package managers to automate the whole process. There are many examples. There are, for example, the distribution package managers. There is pip for the Python world, Conda beyond just Python. And there is one called Spec, which we are using for our purposes. I'd like to introduce that in more detail. It's mainly developed at LLNL, and I will only talk about the user's perspective. To start, I will show you how we can actually work with Spec. So I will switch to the command line and show you how to work with Spec. This is an empty system. We don't have anything yet. How do we get Spec? We can just clone it. It's on GitHub. I will only clone the last commit from the latest release. And it should be yes. So we download it from GitHub. Takes a moment. It will also tell us that we're not on a branch. So the message is a bit long, but we can ignore that. We go into the spec directory and we source a shell script. Sorry, that was the wrong one. And now we have access to the spec command line tool. If we run this like this, we see it has a lot of different features. What can we do with it? We can install software. So for example, we can do a spec install, and then we can specify any name of a package that we want to install, for example, zlib, a widely used compression library. I will start this. The first time it takes a bit of time. What it's doing initially, it's some bootstrapping that we only have to do once, the first time we use spec, so it first downloads all the recipes to compile the packages. Initially, we've only cloned spec, the software itself, but not yet the recipes, how to compile packages. That's the first few lines here. Then it has to do some more bootstrapping so that it can run it all. Afterwards, we'll come to the so-called concretization step. At this point, spec takes our request. So we said we would like to install zlib. Spec calls this an abstract spec. You have to be a bit careful here. Their name's quite similar. So there is spec, the tool with an A, and spec with an E, the request that we would like to install. And spec takes this and computes the full dependency graph, and that is then the concrete spec, and then it will compile and install all these packages on our system. Now that's all done, so it started compiling packages. We can see right now it's working on gmake. In a second it will jump on to zlib. Here's our zlib. Let's have a closer look. What did it do? First, it downloads the source code from spec mirror in this case, and then it runs through a number of steps to compile and install zlib on our system. Now that this is done, let's have a look what we now have. Let me clear the screen, and then we can run a spec find, and that will list all the packages that we have installed on our system. And what have we got? We have the zlib that we asked for in some specific version, and then spec has automatically installed 5 dependencies for us that it needed to compile zlib. Spec, in comparison to most other package managers, is very flexible in that it allows us to compile basically arbitrary versions of any package and allows us to control optional features. To learn more about a package, we can run a different command, spec info. We give it the name of a package. And what can we see? I'm sorry. So we have some description at the top. Then it lists different versions. So far, we did not specify anything. We just got the latest version 1.3.1, but there are others, and we're free to pick any other, and we will go ahead and install 1.2.13 in a second. Then there are optional features. Spec calls these variants. Zlib is fairly simple, so there aren't many, but there are a few examples here. We can turn these on or off, and we'll look at the optimize in a second. And this one allows us to disable optimized compilation. And then at the bottom, we see dependencies for building and for linking. Again, there's not much here for zlib, but for example, there is make as a dependency, and we can also control that. So let's go ahead, install a few more zlibs. We again do spec install. And then instead of just saying zlib, we can specify the version with the add. So we say we would like to have 1.2.13. And then we can also turn features on or off. Many are Boolean features, so we can turn them on with a plus, or we can turn them off with a tilde. So we can, for example, say we'd like to turn off the optimization. We can run this. Spec will again run the concretizer to go from this incomplete spec to a full dependency graph. And once that is done, it will go ahead and install all the packages that we now need in addition. You can see at the top there are some green pluses. These we have already on our system. Spec didn't need to recompile. We've just downloaded and installed a different version of zlib. And if we run a spec find again, we can see indeed we have 2 zlibs and the rest has not changed. I said we can also control dependencies. So let's do that. And before we do that, let me actually show you spec info for gmake. And this looks like before. We have our different versions here. We didn't specify anything. Spec picked 4.4.1, but we can, for example, also pick 4.1. So to do that, I will repeat the spec install command. And then to specify details of a dependency, we use the caret. We specify the name, and then we say we'd like to have version 4.1. We can run this. Again, the concretizer takes a moment to compute the dependency graph. And then once that is done, you will see that the first few packages we can reuse, but then we have to now install a new gmake because obviously we've asked for a different version. And once that is done, we will again install another version of zlib. Here you can see we didn't have to re-download because 1.2.13 we've already downloaded in the previous step, but of course we have to recompile. Let's run spec find once more. What have we got? We have 3 different zlibs, we have 2 different gmakes, and a few other dependencies. Now you may ask, how does spec deal with all these different versions and variants? For gmake it looks somewhat obvious. They have 2 different versions. That's easy to distinguish. For zlib it's not that straightforward. We have 3 different zlibs, one with a unique version, the other 2 are identical. And you may remember we also had the same features. The only difference is they use different versions of gmake. So how does spec deal with that? For that, let's run spec find with a few more commands. We can ask for just a specific package and some details as follows. So what can we see here? Each line is one package. The 3 zlibs are at the top level, and then indented we have all the dependencies for each of the zlibs. And on the left there is a hash that spec computes for each of the packages. How does that work? Spec for the hash takes into account the package, the version, the variants, and then all the information about all the dependencies, including all their versions and variants. So we have a unique hash for each package. If we have a look at the 3 zlibs, they have 3 different hashes. If we have a look at the gmakes, we have different versions here and here. They also have different hashes. If I scroll down a bit, we can see we have another gmake 44 here, and indeed the hash has not changed. And spec uses this hash information to keep track of dependencies and also for the installation path so that we can have multiple installations of the same package without conflicts. We can actually see that if I run a spec location. With a -i, we get the installation location. If we can ask for a package just like this is not unique. There are 3 zlibs. Spec doesn't know which one we're interested in. We have to be more concrete. For example, we can pick a version. There's only 131, so this is unique. And if we run this, we can see where spec has installed zlib2, and we can see there is some prefix information about the system, and then there is the name of the package, the version, and then the long hash. And we can confirm this is the first few characters here. We're not limited to just versions. We can really do anything. For example, we can just say we'd like to see something about speclib that has been compiled with a gmake in 4.1. That also works, and we get a different hash, one of the 2 up here, which we can't distinguish up here. So I've showed you how to use spec, how to install packages. I've not yet showed how to actually use a package that we've installed. That's a bit difficult with zlib because there is no command line tool that I could run. So I will instead install another package, and we'll just install cowsay. That gives us a nice tool that we can run on the command line and see something. Spec has to compile a number of dependencies, so this will take some time. I will switch back to the presentation now and come back to cowsay in the end. Moving on, we've seen how to use the basics of spec. Let's talk about a few other features that are relevant for us on the HPC. First of all, spec supports environments. They're somewhat similar to Conda or Python virtual environments. They're quite useful to group software together. It can automatically generate the module files on the HPC. It supports both TCL modules and hierarchical LMOD modules. We can have local mirrors, either source mirrors, so that we don't have to re-download, or also binary mirrors with pre-compiled software. That is very handy if we repeatedly install the same packages, because then we don't have to recompile all the time, which admittedly can be quite slow. Instead, we can just reinstall the precompiled binary. And it can use external packages. For us on the HPC, it's, for example, relevant that we can use Slurm provided on the HPC, and then we can tell spec about that Slurm, and it will use that, for example, for MPI implementations. This is a primarily Python conference, so you may ask, is spec relevant for Python packages at all? To answer that, let me show you another command, spec list, that lists all the packages spec knows about. We can specify a string, and then it will only look for those packages that have this substring in the name. So for example, the py- conveniently lists all the Python packages because they all start with a py-. So if I run this, we can see there are indeed quite a few. We have around about 2,500 Python packages in Spec. Would I recommend that you switch to Spec for all your future Python work? The answer is definitely no. For most pure Python works and only Python dependencies, working with just a virtual environment, for example, will be much easier and more flexible. The power of Spec will come in if you need Python and non-Python dependencies, or maybe want to compile Python yourself with some optional feature turned on or off. And in that case, one could, for example, imagine a scenario where you install Python itself and other non-Python dependencies using Spec, and then you use the Spec installed Python to, on top of that, work with a virtual environment. To finish off the Spec part, let's have a look at how we can contribute a package. That's fairly easy. Spec is written in Python and also uses Python as the language for the recipes. We can have a look as an example. Here I've picked a simple library, Tomly, the Toml implementation that more recently has made it into the Python standard library. And we have a package.py file here, and we can have a look inside. The main thing is we have one class with our package name. We inherit from one of several different base classes that Spec provides. These base classes are really convenient and really important. They provide support for widely used build systems. So for example, there is one for Python here. There are also base classes for AutoTools or CMake, and Spec then knows how to work with, for example, AutoTools, CMake, or Python, how to invoke the tools on the command line to install libraries. And then we only have to provide some additional package-specific metadata. For Tomly, this is fairly simple. So we, for example, use a helper function version to define different versions. And there is a similar helper function for dependencies. There's not much here for Tomly, but for example, we have Python. We can specify constraints, so we always need at least Python 3.6. We need this both to build and to run the package. And when we have a more recent version of Tomly, at least 2.0.1, then we also need a more recent Python. And all of this and a lot more we can express very conveniently in these package.py files. Moving on to our setup. First of all, why did we choose Spec? Most importantly, it provides the required flexibility. It has a strong focus on HPC, so it provides support for different architectures. We can, for example, compile on PowerPCs. We can compile optimized for different microarchitectures. It has a large stack of relevant software. It's quite actively developed, and the community is quite active, and we can also use it to distribute our own software. And we have contributed to a number of different packages, either support for new packages or fixing bugs in existing packages. To repeat our requirements, we have these tool chains where we want different compilers, either GCC or Intel in different versions. We want to combine these with different MPI implementations, OpenMPI for GCC, Intel MPI for the Intel compiler, and then depending on the tool chain, we have around about 30 to 40 other packages in a tool chain. And we have the pre-compiled applications, so for example, a Anaconda-like Python environment. We have a bit of custom tooling. We track all the details of all our packages and dependencies in a dedicated Git repository. And then we wrote a small Python package that we can use to install the software. This internally uses Spec and the information that we track in the other repository, and will then go ahead and install the software stack. We can have a look at the workflow in a bit more detail. We use Spec environments. We have one dedicated environment for each toolchain. That makes it easy to group all the software for a toolchain together, but keep the toolchains somewhat independent. Of course, the toolchains can evolve over time. People may request additional software, may request that certain package has different features activated or deactivated because they need that for their work. So we also keep track of the toolchains, how they evolve over time. This we do with what we call MPSD software releases, just using the name of our institute. And we basically do this with different Git branches. And then we can use our command line tool, and we can run a single command, MPSD software, we install, then we pick one of these releases, and then a toolchain, for example here a GCC 14.2 toolchain This will download the required repositories, will install all the packages and set up the modules. And so once we have a working toolchain, recompiling the whole toolchain is fairly simple and straightforward, requires little human intervention. We have around about 600 packages in one software release, and we have a somewhat heterogeneous HPC. So we compile for 6 different architectures and or microarchitectures and provide the full software stack on all of these. From the HPC user's perspective, as I said in the beginning, they don't have to know anything about spec or how things work under the hood. They only need to know the module command that they're used to, and then to basically repeat what we saw already, we have the different compilers here at the bottom now. And then I've loaded one, we get all the packages that we've installed with that compiler. I've also again loaded an MPI implementation, and that gives us also access to the packages compiled with this specific compiler version and this specific MPI implementation. Towards the end, let me briefly talk about a few challenges. One of the big tasks for spec is to resolve the whole dependency tree, so the so-called concretization. And this is just a notoriously difficult task, so it's quite easy to request incompatible packages. And spec cannot do much about it other than tell us. It's, however, sometimes quite difficult from the error messages to figure out where exactly a conflict is coming from. This has been improved a lot over time, but it's still at times a bit challenging to understand the error messages. Then there are some problematic mirrors. We, for example, repeatedly observed that some people distribute their software on Dropbox, and we had hit some download rate limits, so we couldn't any longer download towards the mid of the month or so. Also the Intel mirror, where Intel distributes its own software, compiler and MPI and so on, is a bit flaky. There are of course bugs everywhere. Most problematic are bugs in the actual packages, which we sometimes cannot work around without help from the upstream maintainers. The documentation in general, I have to say, is really good. For some details, it's lacking. So at some point, one has to go to the source code and try to understand what's going on. And we're not fully independent of the operating system. So some things, for example, the glibc and some system headers are reused from the operating system. And this can imply that a toolchain that works just fine on one version of the operating system may no longer work fine on a different version. Now I promised I will show Causae in the end. So let's jump back to the command line. And we can say installation has indeed finished. Causae is the last package. Let's run another spec find to see what we have. And we have a lot more now. And down here is our Causae. I need to also prove that we don't have any before. So if we do a which Causae now, there's nothing. To actually use it, we use spec load. And if we do another which Causae, we can see there is one. This is now familiar. We have the package name, we have the version and the long hash. And we can now also use it. So we can, for example, say hello. And indeed, there is our cow to say hello. I've also prepared a different message that we can have a look at. And here's another message.
I modified that. That's an advert. We're looking for somebody to work with data in Python. I thought this was the right place. It's right here. It's about green magnets. The magnets are not green, but for renewable energy, the laser pointer is green. Okay, sorry, carry on.
So we've seen Causae. Let me jump back to the presentation and the summary. So we've seen spec provides a very flexible package management that works well on the HPC, but can work equally well on your laptop or desktop. And if you want to learn more, I would highly recommend that you check out their official tutorial. This goes much more in depth than I could do and is written quite well. Thank you for your attention.
Thank you, Martin. So I'm not sure that everyone heard exactly what Hans said. So maybe if you want to repeat, no, it's okay.
In the slides, there's a position open to work with Martin.
Okay, so maybe it's clearer. Okay, we have time for some questions. Here. Oh.
Thank you, nice talk. I'm wondering, since you're providing all the software for HPC scientists, and they're a curious bunch, like how many of them actually start using Spec themselves, and how many just come to you with, I need version X of package Y?
I'd say most people probably come to us, or if they don't come, or we're too slow, they will just install it themselves, but typically not using Spec. We have a few who are using Spec, and we have also a few who've actively contributed to our work, so helped us fix some bugs in some packages, for example.
Any other question? Okay. Okay, so I guess we can thank our speakers. And again, thank you.